Everyone, let me know if you can hear me. Hope you guys are having a good holiday so far. You guys going back next week, Wednesday, after the long weekend. Ready for term 2. And then, it's a downhill run to mid-year exams, and then after that prelims, and then after prelims it then runs to finals. So I see you guys are starting earlier this year with your May, June exams. It's more like May exams and May and June exams. Can you all hear me okay? Okay, I'll give it like another few minutes, wait for maybe 1 or 2 more people to join, and then I'll start with just some recap of the work that you guys have done for maths. So there's only 3 main topics that you guys covered this term. You guys did sequences and series, and you did inverse of functions, and then you did okay, cool, there's sound, thank you very much. And then you guys did trigonometry, so just some identities that you guys then covered. So I've got some questions here we'll run over. Pardon me. And then, we'll see how today goes. All right. Sorry for being slow with the videos this year. It's just been a crazy start to the year. But I will have the videos up for the May, June exams. Let's have a look here. Numeric patterns including arithmetic, geometric sequences and series, sigma notation, derivation and application of formulas for the sum of arithmetic and geometric. Okay. All right, so I think what I'm going to do is, let me swap cameras around, and then we can start with some sequences and series. Okay, do that over there, this one side, and then just do this. But yeah, how did term 1 go for maths? If some of you might have your marks back, let me know how did term 1's maths and science marks go. What are you aiming for your June exams? And let me know how all that's going. Okay, so let me just open the ATP here. So the first 4 weeks of the term you guys spent on number patterns. Okay, let me just swap the camera around. You know, I was probably just gonna come on. There we go. Let's just swap that around over there. Okay, you guys are staring at my ceiling right now. Let me just swap the camera. There we go. Okay, desk is a bit of a mess over there, but anyway, let's just zoom in. Okay, and just adjust that. Okay, so just let me know if the writing is backwards or if I have to swap things around or anything like that. There we go. Okay, let's find the keyboard there. I think in order for you guys to see properly, I have to do that. Is that better for everyone? Okay, so just to run over sequences and series. So let's do. Okay, sequences and series. So from grade 11, you guys would have done arithmetic, and if I can remember, quadratic. Okay, so arithmetic. Okay, the difference between a sequence and a series. A sequence is, oh, it's upside down. Hold on, let me just. Is that way better? Or do I need to flip the whole thing around this way? Okay, we'll get there. So, with sequences and series, okay, the difference between a sequence and... Oh, what's happening? Oh dear, I think the stand just broke. No worries. There we go. Okay, so the difference between sequences and series, as I was saying, a sequence is a set of numbers, where a series is then where we add up our numbers. So if we start with basics, arithmetic, okay, that just has a common difference. Okay, that we're looking at Tn equals to a, let's see, plus n minus 1 times d. So we have our common difference. A is the first term. Okay, and then if we sum everything up, so Sn is then equal to n divided by 2, 2a plus n minus 1 times d. Okay, that's for arithmetic. Then if we look at the next one, so if we look then at geometric. Okay, so geometric has a common ratio that we are dealing with. So Tn equals to a common ratio n, or to the power of n minus 1. Okay, so this common ratio here is just term 2 divided by term 1, which equals term 3 divided by term 2. Okay, so they like asking this kind of question where they'll give you 4 values, and then one of them will be x, and they'll ask you to find the value of x and so on. Okay, and then the sum of this, we have 2, so we have Sn is equal to a to the power of r to the n minus 1. Okay, and that is all over r minus 1. Okay, so for this over here, a is still your first term, r is your common ratio, and then n is the nth term which we're summing to. Okay, this is for when we're just looking for any specific. So if n equals to 3, we can use this. But the other one that we look at is when we sum to infinity. So s to infinity is then going to be just the first term divided by 1 minus r. Okay, so the reason for that being is the limit. So just an interesting fact here, the limit as n tends to infinity of r to the n minus 1. Okay, so what happens with that? That just ends up tending to 1. Okay, and that's why we then left up with this term over here, where we just have a over r minus 1. So this ends up being 1. Okay. And then let's see, after geometric, we deal with quadratic. Okay, so quadratic, we just look at quadratic formula, so like a parabola. So that's Tn equals to a n squared plus bn plus c. Okay, where a, b, and c are then our what do you call them, your coefficients that you're looking for. This would normally give you the y-intercept, okay, and then in order to find a, we'll have 2a equals to your second difference. Okay, remember quadratic always has a second common difference. And then in order to find b, it's 3a plus b equals to the first term in second difference. Okay, and then a plus b plus c equals to the first term of the sequence. So that equals to first term of sequence. Okay, so why is this? Okay, so if we're looking for the first term, remember when we're looking at sequences, the first position is always represented as the 0th position. So, sorry, we're looking at the first term. Sorry, I'm thinking about coding, which means n is just 1. So we end up just having a plus b plus c equals to our first term. Okay, if we had multiple terms in this sequence. Okay, the reason why we don't have a formula for summing up quadratic, okay, you could do it to a point. So if you look at a quadratic graph, if you look at a parabola, okay, if you look at what's happening over here, let's say this here is the first term, and then this becomes the second term, and the third term, and so on. We can only sum half the graph at a time, because if we have to sum all the terms, you can see that everything is eventually just going to, well, you'll have that term plus that term. Okay, that term plus that term, that term plus that term. So you're duplicating terms within the function itself, because remember, these will be the outputs. Tn is the output of the function. So you would end up duplicating everything up until the turning point, where the turning point will only be once. Okay, so it will be turning point, that value twice, that value twice, that value twice, so on and so on. Why? Because it's spread out on both ends. Okay, so that's pretty much all the formulas that you need to know for sequences and series. Okay, remember, sequences is just a set of number. So sequence is a set of numbers. So 1, 3, 5, 7, 9. Okay, series is where we add 1 plus 3 plus 5 plus 7 plus 9 and so on. Okay, so keeping that in mind, let's have a look at a question where we're dealing with this. Okay, so I'm going to be doing the following question paper. I'll tell you now where it comes from. Okay, let me see. I have it open over here. This is the May, April. I think this is the Mpumalanga paper. Let me just double check here. Yes, this is the Mpumalanga April paper from 2021. So April 2021. That's okay. So let's have a look at the first one. Given the following sequence, -5, 4, 21, 46. Okay, so you can see it's growing quite quickly. Determine the general term for the sequence above. Okay, so if you're not sure with the sequence, the best thing to do is just see if you can find a common difference, find a common ratio, and look at what's happening. So we have -5, 4, 21, 46. Okay, so if I look at those two over there, to go from -5 to 4, we have to add 5, we have to add 9. From 4 to 21, we are then 21, 20, 19, 18. That's 17. 21 to 46 is adding 25. So let's see. 9 to 17 is then adding, adding 8. 17 to 25 is then also adding 8. Yes. Okay, so we know we are dealing with a, go back. dealing with a quadratic number pattern. Okay, so now that we know which number pattern we're dealing with, we can now determine the general term for this. Okay, so we know we're looking for Tn equals to an squared plus bn plus c. Okay, so 2a is going to equal to 8, so a equals 4. Okay, remember 2a always equals to your first common difference or your second common difference. Okay, then we have 3a plus b equals to 9. Okay, so it's that term over there. Okay, and then once we have that, we can then substitute in. So 3 times 4 plus b equals 9. So b is going to then equal to, let's see, 3 times 4 is 12. Take it over. 9 minus 12 is going to be minus 3. Okay, and then finally we are looking for a plus b plus c equals to negative 5. So we have 4 plus minus 3 plus c equals negative 5. Okay, so 4 minus 3 gives you 1. Take it over, becomes minus 1. So c equals to negative 6. Okay, so we then have that Tn equals to 4n squared plus minus 3n, and then that is minus 6. Okay, and then if we look at the next question, it says determine t of 15. Okay, so t of 15, we're looking for the 15th term in the sequence over here. Okay, so we want t of 15, and it's as simple as just plugging 15 into n's place, minus 3 times 15 minus 6. Okay, I'm never going to be able to do that in my head. Let's just punch that into the calculator. 15 squared, and then that's minus 3 times 15, and then that is minus 6. And that gives us an answer of 849. Okay, 849. So you can see that the fifth term, the fourth term was 46. So what's that? 11 terms later, we're already at 849. Okay. All right. Then the next one says which term in the sequence will equal 346. Okay, so they've given us Tn's value. Okay, so we need to find Tn, which equals to 346. Okay, given the formula over there. Let me put this aside. Okay, so we have 346 equals to 4n squared minus 3n minus 6. Okay, now all we have to do is take that over, equal to 0, and factorize. So 0 equals 4n squared minus 3n. Minus 6 minus 346 is going to give you minus 352. Okay, now in order to factorize that, that's going to be a nightmare to try and find the factors of 352 involving the 4 and or to get to 3. So, sorry. So a sip of water, and then what you're going to do is you can use the quadratic formula. Okay, don't forget quadratic formula. X equals negative b plus minus the square root b squared minus 4ac all over 2a. Okay, so just because we're doing number patterns doesn't mean we get to forget about this. So we plug everything in over there. So that's negative 3 plus minus the square root of negative 3 squared. Okay, minus 4a is 4 and c is negative 352. Okay, it's important to note that yes, c needs to be negative, or at least a needs to be negative to cancel that with that negative to give us positive. Why? Otherwise we could end up with a negative number at the bottom here, meaning we have non-real roots. Okay, and that's all over 2 times 4. Okay, so plug that into the calculator. Fraction negative 3. Okay, please use my calculator is quite bad. You can see how worn it is, but please use this negative number when using negative values. Don't use the minus. Okay, that means minus, so the difference, that means negative. Okay, and then let's do plus first. The square root of negative 3 squared minus 4 times 4, and then that is minus 352. all over 4 times 4. Okay, 4.88. So x1 equals 4.88. Okay, and if we check minus 1, just double check everything. Negative 4.5. Okay, so x2 equals negative 4.5. Now we can't have a negative 4.5 term, so therefore we can't use this one. Okay, so therefore we know that in order to get that value up there, we're going to need more or less when n equals to 5. Okay, and you can actually go and plug that in and check which one would be closer, whether it's 4 or whether it's 5. Okay. Let's have a look here. I think let me do question 2 as well from this set because it does deal with the summations. Okay, I know some of you sometimes struggle with the summations. Are there any questions regarding question 1, what I did, and if I need to explain something again, anything you're not sure about? Okay, let's have a look then at question 2. So question 2, they give you the summation over here. So we have the sum from I equals 2 up to m, okay, of 32 times 2 to the power of 5 times minus I, okay, and then that must be less than 500. So it says determine the value of m for which the above mentioned statement is true by using the correct sum formula. Aha, okay, so you should notice immediately that this is dealing with a geometric series. Okay, why? Because it's 2 to the power of 5 minus I, so 2 is the common ratio over there. Okay, but if you weren't sure, write out a couple of these to see what's happening. Okay, so I'll do it on a clean sheet of paper over here. So what I like to do is just to write out a few of them. So we're going to have punch it into the calculator. Remember we're starting at 2, not at 1, so just be careful with that. So 32, 2 to the power of, let's see, 5 minus 2. So the first term is 256 plus, then we go delete 3, 128 plus 4. And then that's 64. Okay, so what you can then do is check to see if there is a common difference between them, but you can see immediately that 64 is half of 128 and 128 is half of 256. Okay, so now that we have that, we know that we're dealing with a geometric. Okay, can't spell today. So dealing with geometric, and we know that we're dealing with the sum of a geometric, so we're dealing with series. Therefore, we know that Sn equals a r to the n minus 1 all over r minus 1. Okay, so we have a, it's 256. We have r, that's given as 2. Okay, so r equals 2. And we are trying to solve for n. So let's just substitute everything in. We know that this must all be less than 500. Okay, so we have 256, 2 to the n minus 1 all over 2 minus 1. Okay, now one thing that you should notice already, 2 or r is not between 1 and minus 1. Okay, so we know that this is not going to converge. It's just going to continue getting smaller and smaller and smaller and smaller. Okay, so we know convergence will not take place. So that all must be less than 500. Okay, now we're solving for n. Okay, so we have 256, and then we have 2 to the n minus 1 less than 500. Why? Because 2 minus 1 is just 1. Okay, so now we can divide 500. So 500 divided by 256, that's going to give you 1.95. So 2n minus 1 less than 1.95. Okay, then take the 1 over, so it becomes plus. So add 1 to that. So we then have 2 to the n must be less than. Let's see, that's 2.95. Okay, and now what do we need to do? We need to get n. So how do we do that? Okay, well, it's in exponential form. Okay, we need n on its own, so we need to convert to logarithmic. Okay, so how do we do that? The method I like to use is I call it the drop and swap. We're going to drop this. That's going to become a base, and then we're going to add log, and then we're going to swap n and 2.95. Okay, so what do I mean? We get log of 2n. Okay, this is technically what I'm doing. Less than 2.95, and then I swap those two around. So it's log, okay, base 2.95 must be less than n. Okay, so let's just double check. Do we swap the sign around when we end up doing log with inequalities? Just double check that. Where's our log rules? Do we swap it? No, we don't. Okay, so we don't swap it. Okay, we just swap the number. So if we then work that out, we are then going to have log. Log base 2.95. Okay, and if we solve that, let's just have a look. Have I done everything correct? Divide that over, gives me that over there. End up with that, take that over. So according to my calculations, we then end up with 1.56 must be less than n. So n needs to be less than 2. Okay, so more or less. Okay, if we, more or less that over there. Okay. Let's have a look. Less than 500, so 256 plus 128. We then get that. Okay, yeah, so we know we have less than 500 over there. So if n is less than 2, we then definitely have that. Okay, doesn't really make sense. I'll have to check numbers. I might have made an error somewhere. But this is pretty much what we're looking at doing. Okay. Same principle applies in order to solve for n, and we're finding which value, and because we need less than, you round that up. Okay, all right, then it says determine the value of s infinity minus s4. Okay, so we can work out s infinity for this one over here. So let's just have a look. What is that asking us? That's just asking us to do the following over here. So we want s infinity minus s4, which is then just going to be a over 1 minus r minus a to r to the n minus 1 all over r minus 1. Okay, so now we just have to substitute everything in. The first value is 256. Let me show you. Oh, pardon me. Okay. Then, hold on. Yep, there we go. It's 256, 1 minus r, so r is 2. And then, yeah, we have minus, I'm sure this is the wrong way around. That should be r minus 1. So this here becomes 2 minus 1. And then over here, we're then just going to have 256, 2 to the power of 4 minus 1 all over 2 minus 1. So then we just have 256 minus 256 times 2 to the power of 4 minus 1. And then if we calculate that, we get an answer of minus 3584. Okay. All right, so that's pretty much sequences and series. Question 3 here is a nice example where you then have to find x. So you can solve for x for an arithmetic sequence. So you just have to plug that into your formula and then determine x. And yeah, so I just wanted to cover those two questions. Pardon me. Any questions on this question so far with the summation? Okay. If there aren't any questions on this, then I think I'm going to move on then to looking at inverses of functions. Okay. I know that is one. It's normally a small question within the paper, but it is a good thing. Oh, well, battery saving mode. Suppose I better plug my laptop in. Okay, there we go. Now I'm not going to lose you guys. So that's pretty much it. Just remember that, where's my page? Arithmetic, common difference. We can sum it up still as a common difference. Geometric, common ratio. And then quadratic as a second common difference. Okay, all right. Let's have a look at inverses of functions. Let's see. I might have to run and go and get some more paper. Let's do this. So if we look at the inverse of a function, what are we looking at? So otherwise what I must do is I must look at getting a whiteboard for live streams, because then I don't have to worry about paper. Okay, so when we're looking at the inverse of a function, the most common one that they are going to ask you to do is to find the inverse of y equals a to the n. The reason why they like doing that, because then this becomes a logarithmic function. So you can find the inverse of other functions, but for instance, you won't be able to find the inverse of y equals to x squared plus 2x plus 5. The reason why is you won't be able to get, remember, when we find the inverse, okay, let me first explain this. So when we look at the inverse of a function, what we are doing is we are reflecting that function over the y equals to x axis. Okay, so that sits at a 45-degree angle over there, and that is where y equals to x. So if I have 1 over here, and you go up there, that value there will then be 1 on the y-axis. Okay, so all we're doing is we're taking our function now, and we're reflecting it, so we are literally folding our paper over that way. Okay, and we're looking at what it creates over here. So the reason why we struggle to do that is because you swap your variables around. So now if we look at this, if I try and find the inverse of that, I'm going to have x equals to y squared plus 2y plus 5. I can't get y over here on its own. Okay, I can have x minus 5 equals to y, y minus 1, but I'm not going to get y on its own. So I can't explicitly write this function as y in terms of x. Okay, but what we can do, okay, so we're not doing that. What we can do is, if we look at the following, y equals to 2x over there, and I say let y equals to x to find the inverse. Okay, remember the inverse is written like this, f negative 1 of x. Okay, this does not equal 1 over f of x. Okay, don't make that mistake. It's not the same thing. Okay, so what we have over here is we then have x equals 2 to the y. Now we can get that on its own. Okay, how do we do that? We have to apply our logarithmic rule. So this is what I call drop and swap. So we drop this to a base and then we swap those two around. So we end up with y then equals to log base 2 of x. Okay, if we want to find the inverse of this, what we do is that we then do the opposite. So we pop and swap. Okay, so then the inverse of this with this whole thing now moves up, and we swap x and y to get back to this over here. Okay, and that's pretty much what we're dealing with the inverse of a function. Okay, you can find the inverse of a straight line, y equals to 5x minus 7. That's pretty straightforward. Y equals to x, so we have, x equals to 5y minus 7, x plus 7 equals 5y, so therefore x plus 7 divided by 5 equals y. What you will notice is the whatever was the y-intercept here, okay, generally gets added on or subtracted from x now when you take it over. Okay, so this here you'll have a gradient which is the inverse of this, so you'll have 1 over 5x plus 7 over 5 as your y-intercept. Okay, and that's pretty much dealing with inverse functions. So, the other thing you have to test when creating inverse functions to check if whether a function is actually a function. So I'll do this at the bottom here. Okay, so how do we check if a function is a function? Okay, in order to do that, we have to do the straight line test. So if you have a parabola like this, we know it's a function because it passes the straight line test. If I draw a straight line down, it only cuts it once. Okay. If I draw a logarithmic function, we know it's a true function. It only cuts once. Okay. But if I draw the following, okay, this is not a function. Why? Because it straight line test fails. Okay. It cuts more than once. This is then dealing with two variable functions, which you guys don't have to worry about now, but for a single variable function, this fails because the straight line test cuts twice. Okay, all right, so let's have a look then at question 5 here. I'm going to squeeze it on the side of the page. Okay, so question 5, let me put this here. Let me read it first. So question 5 says, given the function f of x equals to 2 to the power of negative x, determine the inverse of the function in the terms of y equals to that. Is g a function? Okay, we'll go over that, give a reason for it. And then it says draw a sketch of the graph f and g on the same set of axes. Okay, so having a look at that, let's have a look at the inverse of this function. Okay, so we are given that f of x equals to 2 to the negative x. Okay, so how are we going to go about doing this? Oh, this paper is the Free State 2020 prep exam. So if you want to find the paper, it's just Maths Paper 1, Free State, September 2020 prep paper. Let me just check here. Yeah, it's a Free State paper. That's what I'm looking for. So to find the inverse of this function now, yes, we are dealing with a negative. So what we can do is we can drop this down. So we can say that f of x equals to 1 over 2 to the x. Okay, more than welcome to do that. Okay, because all we've done is we've taken this down. But it then makes the, how can I put it? It can get complicated because we have x at the bottom, but we also know that 1 to the power of anything is just 1. So this is also equivalent to a half to the power of x per se. Okay, so now that we have this, we can then find the inverse. So this might make it a little bit easier because then you don't have to deal with the negative when you swap things around and so on. Okay. So looking at that over there, hold on. I just want to check something. Okay, so you can do it this way, or we can just use this function over here. I'll show you both ways. Okay. All that's going to happen is this one's first going to produce a negative log function, and then you're going to get rid of the negative log function by creating a half. Okay, so let's do this one on the right first. So we want to let y equals to x and then find the inverse. So we have x equals to a half y. Okay, so now we're going to drop and swap. So then we have y equal to log of a half x. Okay, that's the inverse. That is then equal to g of x. Okay, and if we use then this method over here, or this way, we're then going to have again y equal to x. So just make sure you state that. And then we are going to have x equals to negative y. So now we drop and swap again. So we end up with negative y equals log base 2 to the x, divide by negative. So y equals negative log 2x. Okay, so you get there, but now we're dealing with this negative value over here. In order to get rid of this negative value, all we do is we invert the base. So by doing that, okay, so if you want a general rule for it, I'll write one now, but that becomes log, not the half, that becomes, or not the minus, that becomes a half x. So if you have y equals to negative log a to the b, okay, it then becomes y equals log 1 over a b. Okay, so all that happens is you invert your base over there. Okay, all right, so that's just log rules over there. Okay, probably just one that you'll have to just look up. I'm not sure if they always give you this one. Okay, so maybe if you're not sure about it, ask. Check with your teacher to make sure that you've covered this in class, because they like asking this, especially in the finals. They'll give you something like this just to test your knowledge. Okay, and then it says give a, or is g a function? So is the inverse, okay, so this equals g. Is it a function? Okay, so we can check that by drawing it. Okay, so if we go log of 0.5 and we substitute in 0, we should get undefined, right, 1. Then we get 0. Okay, so we know we're still cutting at x equals to 1, so the function's going to then do that. Okay, so the base just controls the steepness of the graph, and you can see by drawing a straight line down, it passes the straight line test, so yes, it is a function. Okay, any questions on finding the inverse? Any at all? Any questions so far? Okay, and then the next one says to draw. They want us to draw F and G. Okay, so just to give a sketch. Okay, so we have okay, so we have half over here. Okay, so sorry, I lost my train of thought there. I was just checking something on the side. So a half over here. Okay, so we know that when we draw this function over here, if we want to find the y-intercept, it's where x equals to 0. Anything to the power of 0 is 1. So we're going to have this function cutting over here. Okay, and then if we reflect that over the y equals to x, we get g, and g looks something like that. Okay, so that's the logarithmic function. That's the exponential function. See, we have a question asking about a composite function. So a composite function is when you have a function within a function. So composite would then be this. Okay, so that is when you have f of g of x. Okay, so we have a function within a function. So let's say we have f of x equals 2x and g of x equals 2x squared plus 7. Therefore, if we then find the composite f of g of x, okay, that's just going to then be 2 times, now wherever x is, we substitute g in, so that's 2 times x squared plus 7. That's what a composite function is. Okay, so it's just multiple functions. You can have as many as you want within each other. All it does is it just produces a new function. But you must be careful because the composite function, you still have to take the domain and range of these two functions into account. Okay, so the domain and range of these two functions will determine the domain and range of the composite function. You don't treat it as a separate function. Okay. All right, and that is inverse function. So as I said, not too complicated in that sense. They do like asking logarithmic to exponential or exponential to logarithmic because they want to check your knowledge of if you can convert from log to exponential and from exponential to log. Okay. All right. Let's see. What else? Okay, then the last section for maths for term 1 was trigonometry. Okay, so if I look here, it was just going over trigonometry, composite angles, and identities. So you're looking at the double angle for sine and cos. You're looking at the different ways the cos double angle can be written, and then revised proof of sine cos area rule. Okay, I'll go over that, and then solve problems in 2 and 3 dimensions applying the sine cos area rule. Okay, so let's see, it's cos and area rule, not this here. Okay, let me just have a look here. Okay, I'll use the back of this page here. So, looking at trigonometry, okay, so I know it is a section that everyone seems to dread. I'm not sure why. Okay, I think the confusion comes in with the cast diagram and identifying when it's positive, when it's negative, transformations and everything. So I think what I'll do is I'll just give a brief overview of trig. Okay, and then we will then have a look at the area rules. Okay, so with trig, okay, we deal with 3 trigonometric functions. Okay, we deal with sine graph, which looks like this. Okay, we deal with cos graph, okay, which looks like this. And then we deal with the tan graph, okay, which then has asymptotes, so it looks something like that. That's tan of x. Okay, and then we end up using this cast diagram. That's A, C, okay, 0, 90, 180, 270, 360. Okay, now the cast diagram is just a condensed version of your graphs. That's all it is. Okay, so if we go 0, 90, 180, 270, and 360. So I just want to explain it. So if we have a look at the sine graph over here, why is sine positive between 0 and 90? Well, if you look at the graph, it's above the x-axis between 0 and 90. Why is it positive between 90 and 180? Because sine is positive, it's above the x-axis between 90 and 180. Okay. Why is it negative in the third quadrant? Because it's below the x-axis between 180 and 270. And it is negative in the fourth quadrant because it is below the x-axis, okay, from 270 to 360. Okay, so all it is we're taking that and we're looking at that. Okay, same with cos graph, that's 90, that then becomes 180, 270, and 360. Okay, so cos is positive in the fourth quadrant because between 270 and 360, it's above the x-axis. Okay, it's positive in the first quadrant because, again, it's above the x-axis between 0 and 90, and then between 90 and 270, you can see that the whole thing is negative. That's why it's negative in those two quadrants. And then the same happens for the tan function over here. So 0 and 90, positive. From 90 to 180, it's negative. From 180 to 270, it's then positive. It's above the x-axis here. And then between 270 and 360, it's below the axis again. Okay, so that's the cast diagram and that over there. Okay, so just to look at the double angles that you're dealing with. Okay, the only thing that you have to remember is the sign change that happens between sine and cos. Okay, I just want to sort the dog out that's dreaming downstairs. Gotta love watching a dog sleep sometimes. They do some funny things. Anyway, so getting back to trig. So using your functions is sometimes better. I prefer using the functions or graphs than using your cos diagram, because then if we look at, for instance, if they give you cos of x plus 90, why does this not change? Okay, well, we know that if we look at a function, x plus something means we've shifted the function to the left. If it's plus, we move left. If it's minus, we move right. Okay, so all that's happened there is, okay, we've taken all our points of our graph, okay, and we've shifted them 90 degrees to the right. So now we then have this point moves 90 degrees, so now it's there. This point, this point here moves 90 degrees, so now it's up there. Okay, this point now moves 90 degrees, so it's there. This one moves over, so it's there, and this one moves over, so it's there. So you can now see that we are dealing with a negative sine graph. So this becomes a negative sine of x. Okay, so I prefer using this than trying to figure out from the cos diagram what happens to the changes over there. Okay, but let's have a look at the double angles quickly. So we have sine of a plus b plus minus. Okay, we'll do both. That's equal to, okay, so sine a cos b, then plus. So whatever the sign is in the bracket, if it's plus, it stays plus. So then we have sine of b cos of a. Okay, if it was minus, then this just became a minus over there. Okay, but with the cos rule, a plus b, the sign swaps now. It now becomes cos a cos b minus sine a sine b. Okay, now what you should notice is over here, if b equals a, so that equals to a, then we're just going to have two identical things here. So this becomes, then the sine rule will become 2 sine a cos b, or 2 sine a cos a. Because it will then be identical. Okay. And then over here, if b equals a, then we'll have cos squared minus sine squared. Okay. Now, what do we notice? So this is what I'm saying. If we have sine of 2a, then we just end up with 2 sine alpha, or a, So this is just a plus a. So what you then end up with is sine a cos a. Okay. And then with this one over here, okay, this one, if we have cos of 2 alpha, so cos of 2a, or alpha, whichever, what happens is we then end up with cos a minus sine a, so that's equal to cos squared a plus, minus sine squared a. Okay, and from there we know from our other identity sine squared a plus cos squared a equals 1. Okay, so therefore we know that sine squared a equals 1 minus cos squared, so we can then substitute that into here. So we could end up then with the following, cos squared a minus 1 minus cos squared a. Okay, and then we would be left with minus and minus becomes a plus, so 2 cos squared a minus 1. Okay, and then you could actually substitute, instead of in sine's place, you could substitute the expression 1 minus sine squared a into cos's place, and then you would get the identity of 1 minus 2 sine squared a. Okay, so that's how you prove those identities from the cos double angle. Okay. And then the other rules that you need to know for sine and cos, that when calculating area for triangles. Okay, so if you have a triangle, it doesn't have to be a right angle triangle. Okay, we have A, B, and C. And let's say we have capital A, capital B, capital C. Okay, the sine rule states that you can take the opposite side. So you can have A over sine A is equal to the same ratio as B over sine B. Okay, so it's always the angle opposite the side. Okay, which is equal to C over sine of C. Okay, so those will always hold. You can write it that way, or you can write it the other way around where you inverse it. So you can say sine of A over A equals sine of B over B, as long as you keep it consistent. Okay, you can't have this over here. That is not equal to C over sine of C. Okay, no, don't do that. Keep them consistent. If you have all the signs at the top, keep them at the top. If you have the letters or the numbers, those sides at the bottom, then keep all of them at the bottom. Okay. And then we have the cos rule. Okay, so the cos rule is normally when they give us two sides. So when they give us something like this, they give us an angle, theta. They give us B and C, and they want us to find G. Okay, so it's always the angle opposite, or the side opposite the angle given, and then we have two sides on either side of the angle. Okay, so cos rule says that G, it's G squared equals D squared plus C squared minus 2 DC cos of theta. Okay, so if you wanted to find G, you would then square root both sides. You can also use this rule to find the angle. If you have all three sides, you want the angle, and so on. Okay, so that there is then the cos rule, or the cosine rule, whichever one you want to use. Okay. All right, so that would come into play. Let's say we had the following angle or triangle over here. Let's say we have this here. We don't have that angle. That's theta. That's 30 degrees. Let's say that there is 7. Let's see. That's beta. This is, I don't know. Let's make this 11. and make this 5. Okay, I'm just making up these numbers, so we're going to get funny answers here. Okay, they give you something like this, and they want you to find, sorry, let's take that away. Let's say this is x. So let's say they give us the following of there. They ask you find beta, find theta, and find x. Okay, multiple ways of going about this. So you can find beta. Okay, so we find beta using the sine rule. So we can say 5 over sine of beta equals 7 over sine of 30. Okay, which means that that goes up, that comes down. So we have 5 sine 30 all over 7 equals sine of beta. Okay, so beta is then going to equal to, let's see, shift inverse of sine, that is then fraction 5 sine of 30 all over 7, 20.9 degrees. Okay, so now we have beta, so you can find theta using angles of a triangle. So theta could equal to 180 minus 90, minus 30 minus 20.9, which then equals 0 minus 30 minus 20.9. So that's 129.1. You could do it that way, or you could do cos rule. No, I can't use cos rule, sorry, because we don't have x. You could use sine rule again to find theta. Okay, but now to find x, now that we have theta, we can then use the cos rule, or we can use sine rule again. Okay, it's always interchangeable, whichever one you're more comfortable with, but in this case, I'm going to use cos rule. So x squared equals to 5 squared plus 7 squared minus 2 times 5 times 7. That's cos of theta is 129.1. Okay, which means that x, if we plug that into the calculator, so square root 5 squared plus 7 squared minus 2 times 5 times 7 cos, sorry, that's sine, cos of 129.1. And we get a side of 6.16, so roughly 6 units. Okay. All right, so that's pretty much the trick that you guys are to know. Okay, the double angles over here you'll use, or over here, you'll tend to use in proving identity. So they'll ask you to prove the left-hand side equals the right-hand side, and so on and so on. Okay. All right. Let's just take a 2-minute break. I'm going to go and get paper quickly and just fill my water bottle, and then I will be back and we'll run over some physics. So I'll see you guys now. Just give me 2 minutes. All right. Okay, so can you please explain how BSc Physics works at UP? I'm planning on applying for it next year, BSc Mathematics. What is the requirements? Okay, so University of Pretoria has two programs you can do. Okay, they've got the 3-year program and then they've got the 4-year program. So I did the 4-year program for BSc. BSc is generally a 3-year degree. Okay, the 4-year program is what they call the extended program. So in order to get into the 3-year program, you need an average of 65 for both maths and science. Okay, and I think it's 30 APS points. Okay, so that's the key thing. Is maths and science needs to be above 65. If you want to do the extended program, that's what I did. You then need an average of, I think, between 55 and 60, or I ended up with 60 for maths in matric. So with that, I got into the extended program, and then my physics mark was high enough. I remember I finished with, I can't remember, I think it was almost a 70. But fair warning, for maths and science, it becomes a lot more theoretical. Okay, so where's my, I'll find my textbook quickly, or one of them. So with maths, you then start doing a lot more proofs. So you'll see in first year, the first semester, you start with what we call pre-calculus, which pretty much runs over the entire of your matric work and then a little bit more. So you'll go into things like absolute values. So for those who take AP Maths, those students tend to find it a little bit easier because they've covered quite a bit of the stuff in AP Maths. So you start doing limits and things like that as well. But overall, if you are disciplined enough to ensure that you keep up with the work, attend classes, go through the work yourself, you'll be fine. Mathematics, your core modules will then just be your all the maths modules that are there. So calculus, pre-calculus, linear algebra, numerical methods. You learn some programming along the way, and then you can pretty much branch out. So I did physics, BSc Physics, physics as first major, and applied mathematics as second major. So you get theoretical, and then you get applied, or you get statistical. So I did applied math, so that does differential equations, that does linear algebra. So I didn't do statistics or anything like that. I'm not a big fan of statistics. So then that focuses on those kind of things. Yeah, so if you have any more questions regarding that, or if you want to know what the kind of work is that or you might be expected, send me an email. My email is on my YouTube page. So drop me an email and we can organize a chat if you want via Google Meet or whatever, and you can then discuss what you want to do and so on. It does get difficult, but if you keep up with the work and keep focused, then you'll be fine. I had to do it during lockdown, so that wasn't the greatest. I won't lie. There were times where I questioned doing the degree. But now with everything back to normal, with me doing the engineering degree, it's much nicer because you're seeing people in person again. So it's one-on-ones, it's being in a big lecture hall again and so on. But anyway, let's move on to physics. So let me just get the ATP for physics quickly. So week 1 and 2, you did mechanics. Week 3, 4, 5, mechanics. And then started organic chemistry. So I'm not going to cover organic chemistry now. I don't even think an hour would be enough to cover all the organic chemistry because it's such a big subject. Okay, so I'm just going to focus on momentum and impulse and then vertical projectile motion. Okay, so momentum and impulse. So if we look at that, last year you guys looked at free body diagrams and you looked at Newton's laws. Why am I using a normal pen? Looking at Newton's laws. Okay, so Newton's laws, we looked at Newton's second law, which says that the net force acting on a system or on a body is equal to the mass times its acceleration. Okay, so now what we are going to look at, how is the force related to things like speed, how do we calculate things like that. So we have acceleration. We know that acceleration equals velocity over time, change in velocity over change in time. So we are going to use that to calculate then impulse, and you'll see that we get momentum from forces. Okay, so momentum, which is represented as P, okay, is equal to the mass of an object times the velocity at which it moves at. So you'll see that momentum is a vector. Okay, why the direction does take, or it is important which direction it's moving. So you have a scalar multiplied by a vector over there. Okay, so going back to the net force. So if we look at the net force over here, equals to mass times acceleration. We know that acceleration is equal to the change in velocity over change in time. Change in velocity over change in time. Aha, so what do we technically, not P, T. So what do we technically have here? We have that our net force acting on an object is equal to the change in momentum divided by the change in time. Sorry me. Or the more fancy way is if you take the time derivative of force, is it the time derivative? No, because that means you're taking the derivative. If you integrate, sorry. So the derivative dt of velocity gives you acceleration. Derivative is gradient. Instantaneous gradient at a specific point. So if we integrate that, so integration, it's that funny S symbol some of you might have seen, is the opposite of a derivative. So the integration of acceleration gives you velocity. What does that mean? You would have seen from your velocity time graphs that you guys did last year for equations of motion. Let's say you had position delta x first time. If that was constant, then your velocity time graph was 0. Why? The derivative, the derivative of the gradient of a constant function is 0. Why? Because your y value is not changing. So you have y1 which equals y2. Okay, so you have y1 minus y2 over x1 minus x2. This is just equal to 0, which means your acceleration time graph then became 0 as well. Okay, so now if we work backwards, the integral of something, okay, so just some additional mathematics over here. You guys don't have to know integrals, but it's just for interest sakes. The integral is the area under a graph. So if you take the area under a constant function, you will then get a straight line. If you take the area under a straight line, you'll then get a parabola, and so on. If you take the area under a parabola, you'll get a cubic function. So this is the integrals, how they move along. So constant, straight line, parabola, cubic function. If you take the derivative or the gradient of these functions, if you take the gradient of that, it then gives you that, which then gives you that, which then gives you that. Okay, and that's where these came in, all your graphs. Okay, so anyway, taking a complete tangent over there. The net force of an object looks at the change in momentum over a given period of time. Okay, so when we're dealing with impulse is how long something is in contact with something else for, and we look at how the forces come into play. Okay, so if you take the change in momentum, it's then equal to the net force multiplied by the change in time. Okay, so let's prove and show that this is true, okay, using units. Because I think often a lot of you forget to check your units and see what's happening. Okay, so momentum is given as kilograms per meter, kilogram meter per second. Okay, so this has got to be equal to that. So force is measured in newtons, and that is times seconds. But what is a newton actually? A newton is mass times acceleration. So that is kilograms per meter over seconds squared multiplied by seconds. So seconds will cancel out with 1 over there, and we are left with kilograms per meter, or kilogram meter per second. Okay, so we show that our units work as well. So why is it that whenever when they design a car, okay, when the car is traveling, or the front of the car always has what we call a crumple zone. So why do we need a crumple zone? Well, if you increase the contact time, look at your formula here. Force equals change in momentum over delta t. If you increase your contact time, your force must decrease. Okay, so they're inversely proportional. So if you have a car and it has a large crumple zone over here, okay, when it's in an accident, that's going to then crumple down and it's going to keep you safe, okay? But if it has a small crumple zone, okay, think about a piece of paper. You take a piece of paper over here and probably demonstrate it. So if I have a large crumple zone, there's more time where the force is in contact with it for it to then crumple down, okay, to dissipate the force. So your momentum slows down, okay. Whereas if I have a short crumple zone, let's do something like this, okay. If I have a short crumple zone, there is less time that something is in contact with, or the force that's in contact. So therefore, less time means a higher force, okay, to dissipate your momentum. So it is important that if you want to be safe in a car, you design a crumple zone that will increase the time of the contact, okay, so that your force decreases. Okay, so that's pretty much what impulse and momentum looks at. You're looking at decreasing the force by increasing the contact time. So let's have a look here. I think I've got a question. I do. Any questions on my little explanation, if any of you have? Okay. So a ball P with mass M is initially rolling to eastwards when it collides with an identical ball Q, which is rolling westwards. Okay, so we have a ball rolling east, northeast, and a ball rolling west. They are identical, as they state here. Identical masses. So that's M and that's M. Okay. Which is rolling. Okay, so P has a mass of M with the initially rolling east when it collides with identical ball Q, which is rolling westwards at 15 meters per second. Ignore the rotational effect of the ball and the friction. Okay. The graph below shows the velocity of ball P. Okay, so it shows the velocity of ball P. So ball P is moving at a constant velocity for the first second at 10 meters per second. So it's going 10 meters per second to the right. And Q is moving at 15 meters per second, -1 to the left. Okay. After the collision, okay, so this here where it drops off, that will be your contact time. You can see your velocity is changing, so the balls are coming into contact with each other, and then we're changing velocity. And then because velocity is negative, ball P, which is moving this way, is now colliding and moving this way. So both of them, this is what's pretty much happening. Sorry, I'm trying to watch this whole thing on the screen and it's messing with my head. So they come together and then move off as maybe one or separately like that. Okay. All right. So define impulse in words. So impulse is you can look at it, the amount of time that the force spends in contact with an object. Okay. Calculate the velocity of Q after the collision. Okay. So what are we doing here? Oh, I forgot to explain. I apologize. The other thing with impulse and momentum is conservation of momentum. Okay, so conservation of momentum says the change in momentum initially equals the change in momentum final. Okay, so if we look at that, we are looking at mass 1 V1 plus mass 2 V2 initial equals mass 1 V1 plus mass 2 V2 initial final. Okay, so this is what's happening. So we can use this in order to calculate the velocity. So calculate the velocity of Q after the collision. So we can look at the conservation of mechanical energy. Conservation of momentum, not energy. You could use energy, I suppose, if you wanted to, but we're not doing that. Okay, so M1 V1 plus M2 V2 equals to M1 V1 plus M2 V2. Okay, so we know that mass 1 and 2 are the same, so the masses are going to cancel each other out. So we just have V1 initial is, I'm going to take right as positive, so 10 minus 15 meters per second, negative 1, okay, equals to V1 plus V2's final. Oh, sorry. We're looking for V2 final. We have V1 final. We know that that is approximately, that's 10, 9, 8. Let's see, 2, 4, 6, 8. Yeah, there we go. So counting in 2. So 2, 4, 6. So it's now moving minus 6 to the left plus V2. Don't forget your signs. Okay. So therefore we have 10 minus 15 gives me minus 5 meters per second, negative 1. That's minus on that side, bring over plus 6 meters per second, negative 1 equals to V2. So therefore V2 equals to 1 meter per second, negative 1. Okay. So that's calculating V2 over there. It is observed that the kinetic energy of the system decreases. Okay, I'm not really going to focus on kinetic energy. I just want to look at the momentum questions. So I'm going to move to question 3.4. Consider the initial momentum, final momentum, and change in momentum of the ball. Which of these three vectors represent the resultant vector of the two? Okay, consider the momentum, the initial momentum, okay, the final momentum and the change in momentum. Okay, so let's see. 1 had a momentum going this way. 2 had momentum going that way. But 2's was, so P2 was greater than P1. So therefore the resultant momentum is that one over there. Okay. Which one of these vectors represents the resultant vector? That would be the change in momentum. So change in momentum would then be F net. Okay, so as we saw there, over T, so the change in momentum equals the resultant vector. So that would be the change in momentum. And then draw a vector diagram to represent your answer in 3.4.1. remember to label the vectors in your diagram. Okay, so this is pretty much it. So this becomes P2, that's P1, and then that's PR, your resultant vector over there. Okay, so that's pretty much impulse and momentum. The key thing is to remember that momentum is just mass times velocity. Okay, so P equals mass times velocity. It is a vector. Don't forget that. It is a vector. And then if you take the rate of change of momentum, it is then equal to the force applied to the system. Okay, so not a very difficult section over there. Okay. But it does tie in with your kinetic energy, mechanical energy, and so on. So if they ever give you a question where a bullet is shot into a block, you know that you can use conservation of mechanical energy, and the one that everyone forgets to use to calculate their velocity, conservation of momentum. So don't forget, just because you're dealing with equations of motion doesn't mean you can't use kinetic energy or mechanical energy or change in momentum or anything like that. Okay, so everything links into everything else. All right, so let's have a look at vertical projectile motion, because I think this is also, some tend to get a little bit confused about this. Sorry about that. So looking at vertical projectile motion, all that's happening is we are going from horizontal motion. So think of it as this. You throw a ball. You throw a ball to the right. It's got an initial velocity. It's covering a certain distance, delta x. It's got some acceleration. Okay. And there's a given time frame that you're dealing with. Now all that's happening is we are going vertical. Okay, so the only thing that changes here, okay, is your acceleration is now given as a constant acceleration, unless they ask you to calculate a different acceleration. But all that happens in your equations of motion is A is now equal to G, which equals to 9.8 meters per second -2. So it's just a gravitational acceleration. So also, I don't know why some teachers say it's fine to use delta x. I have no idea why. If you draw a graph, this is the x-axis, this is the y-axis. Anything moving up and down is related to the y-axis. Anything moving left and right equals to x-axis. So when you're doing vertical projectile motion, please use y or delta y. Do not use x, because you're going to get used to this now. You then go and study, and you use delta x when you're talking about vertical things, and they just give you 0 because they see that you don't understand the work. Okay, so please use y. So your equations, v final squared equals v initial squared plus a delta t, that stays the same. Then we have v final equals v initial plus 2a delta y. Okay, so a is just g. Okay, don't make that mistake. And then we have delta y equals v initial t plus a half a, which is g delta t squared. Okay, so those are the three main ones that you tend to use. Okay, take gravity, so take downwards as positive. Okay, it sometimes does make it easier. If you take down as positive, then you'll never get g wrong, because g will always be positive. Okay, unless now they've changed the direction, but take down as positive so that g is always positive when a ball's moving down. Okay, or just generally take, I don't want to say take g in the motion, in the direction of the motion, because if a ball goes up and then down, you're going to say that's positive, but then that's also positive, and no. Okay, so just pick a direction and stick to that. Okay, so if we have just a basic example, so let's say we have a ball that is dropped off of a or thrown up off a building. Okay, the ball has an initial velocity of 2 meters per second, -1. It travels for, okay, we want to know, or h is 10 meters. Okay, then we want to know what is the maximum height off the ground. So we want to know h max. Okay, what is that equal to? And then the velocity when the ball hits the ground. Okay, so what do we take into account here? Well, we have the initial velocity. Okay, now one thing that you need to remember is that when we have a parabola, okay, line of symmetry, this side is equal to that side. So the time in vertical projectile motion, the time it takes for it to go from here back up to here, delta t, is equal to the exact same time to go from here to here. Okay, so that line there, delta t, are the exact same. So we have all the information we need in order to calculate the maximum height. Remember, h max is going to be h of the building, so 10, plus this little height over here. So let's call that delta y, plus delta y. So we want to find delta y. Okay, so we also know that when the ball reaches its maximum height, the ball comes to a stop. So what happens, I'll just use this here, the ball gets thrown up. When it reaches its maximum height, okay, it changes direction and then comes back down. So at maximum height, the velocity is 0 because the direction has changed. So it slows down, comes to 0, and then changes direction and comes back down. So at the top there, we're going to have v final equal to 0. We have v initial, so we can work it out. So we can use v final equals v initial plus 2g delta y. Okay, we have v final. Okay, we know that v final is 0. V initial is moving upwards. I'm taking down as positive, up as negative. So moving upwards at 2 meters per second, -1, plus 2 times 9.8 delta y. Okay. Sorry about that. Let me just double check that I have my formula correct here. I have it wrong. This one is squared. Sorry. I thought I had it wrong. So just fix the mistake here. That's not squared. But this one is squared. Okay. So therefore that there must be squared. So what do we have? We have 4, or we have up is positive, down is positive. Okay, so therefore, because it's moving up, your gravity has to be negative, and that also has to be negative, but doesn't matter because of the square. I think I'm off the page. There we go. So what do we have? We have 4 on the right-hand side equals to -2 times 9.8 delta y. So therefore, delta y equals to, let's see, 4 divided by 2 times 9.8. Which then gives you 0.2. Delta y is 0.2 meters. So therefore, our h max equals 10 plus 0.2 meters. Okay, which is then equal to 10.2 meters. Okay, it's not very high actually that this ball gets thrown. Now we want to know what is the final velocity at the bottom over here. Okay, so you can use the total height. You could use this formula over here. Delta y equals VIT plus a half g, delta t squared, but we don't have the time, okay, to travel down, so we can't use that one. We have the total height now. We have the velocity. The initial velocity is 0. We can calculate the final velocity, so we can then use, let's have a look at our formula sheet. Let me just check mine here quickly. Come on. We can use the same formula, we can use the same formula we've just used. Okay, so just be careful, because this is one of the cases where you can use the same formula twice, but it's not always that you can use. There's not one formula to solve everything in vertical projectile motion. Okay, so again, we can have v final squared equals v initial squared plus 2g delta y. We have delta y, we have g, we have v initial, we want v final. So v final equals the square root of 2, 9.8, 10.2, and that's just then going to give you square root of 2, 9.8, 10.2. That's going to be our velocity of 14.14 meters per second, -1. Okay. All right. So just an important thing to keep in mind, you don't use one equation to solve everything, so be careful. I know the equation that everyone loves is this one over here to try and solve everything. Okay, but you can't always use that one. Okay, or the one that I've just used. So always check what's given. If they want time, you can use this one or this one, but provided they've given you the height. If they've only given you the initial velocity and they want time, you have to use the first one. If they've given you the displacement and the initial velocity and they want time, you can use the third one. Okay. If they want displacement, but they haven't given you time, then you know you have to use this second one over here. Okay. So that's pretty much it for vertical projectile motion. Just remember that if they give you one where you have a hot air balloon, okay, a hot air balloon moves up at a constant velocity. So what happens is, okay, I've got a funny hot air balloon. What happens is the object's initial velocity, so v of hot air balloon, v of object, okay, will be the same. So v of object equals v of hot air balloon. Okay, at the beginning. Okay, now when you drop it, this is going to make a little arc and then come down. Okay, so when it moves up, okay, it's a bit difficult to show it here, but what's happening is it's moving up, moving up, moving up, and then it's still moving with a constant velocity. Okay, so Newton's first law comes into play, inertia. So it carries inertia, gravity takes over, and then it pulls it back down again. Okay, and then it falls down. So that's all that. I see everyone's left the stream already, so I think I'm going to stop the stream there for today. I hope everyone enjoyed it. If you have any questions regarding anything, please leave them in the comment section down below. This video will be up. If you have any other questions, please post them in the comment section, or otherwise email me, and I'll get back to them as soon as I can. And remember, let me just change the camera. Wait. Swap the camera around and I can chat to everyone. Okay, I need to fix my setup over here. See. Yep. Oh dear, this whole thing's collapsed. That's what happens when you try and build things yourself. Okay, so if you guys have, if you guys have enjoyed today's stream, then please leave a thumbs up on it. It does help me out a lot. If you have any questions, leave them down below. I'll get back to them as soon as I can, or otherwise send me an email and I will answer those questions with future streams as well. If you guys do have specific questions you want me to go over, send me an email with the question in it, and then I can go over it. And then, yeah, I can answer your guys' questions as well. Otherwise, I'll just set up like I have where I'll do past paper questions and explain the concept. So I do want to do live streams before the finals, but I am also looking at setting up a member thing on my channel. So I'll let you guys all know about that once I have that up and running. Okay. All right. Remember, it's never too late to have an OIC moment, and I'll see you guys in my other videos. Enjoy. Bye-bye.